There is a place in our solar system that no human will ever stand on, not because it's far, but because it's lethal. Venus, our so-called sister planet. Nothing survives there. And yet, more than 50 years ago, the Soviet Union sent a series of spacecraft straight into that nightmare. Venera, the first human-made machines to ever enter the atmosphere of another planet. The first to send back photographs from a world that isn't Earth. But here's the part almost nobody knows. Those discoveries were scattered across Cold War archives, fragmented mission logs, and images that barely survived transmission through an atmosphere dense enough to behave like a liquid. This is what the Soviets really found on Venus, and why it might be the clearest warning about our own planet's future. Let's start by understanding just how difficult it is to land on Venus. The Soviet Venera program began in 1961, just 4 years after Sputnik became the first artificial satellite to orbit Earth. At that time, very little was known about Venus beyond its position in the sky. Scientists believed that under its thick cloud cover might be a world not too different from Earth. Perhaps a temperate climate, maybe even oceans. The atmospheric pressure was estimated to be around 1 bar, similar to Earth's surface. They were spectacularly wrong. The first real data came in October 1967, when Venera 4 became the first spacecraft to successfully enter the atmosphere of another planet. The probe was equipped with parachutes to slow its descent, and it carried instruments to measure temperature, pressure, and atmospheric composition as it fell toward the surface. At first, the readings were encouraging. The temperature was around 30 degrees Celsius. The pressure was similar to Earth's. But as Venera 4 descended deeper into the atmosphere, something unexpected happened. The temperature began to climb. 10 atmospheres of pressure became 20. 20 became more. The readings went beyond anything the Soviet engineers had anticipated. And then, suddenly, all communication stopped. The last measurements showed a temperature of 250 degrees Celsius and a pressure of 22 atmospheres. The spacecraft had been crushed and melted, still kilometers above the surface. It never made it to the ground. This changed everything. When the American Mariner 5 spacecraft flew past Venus, the day after Venera 4 arrived, it confirmed what the Soviets had discovered. The surface pressure on Venus wasn't 1 atmosphere. It was somewhere between 75 and 100 atmospheres, far beyond what any spacecraft had been designed to withstand. The Soviets had severely underestimated Venus. The planet wasn't a tropical paradise hidden beneath clouds. It was hell. After Venera 4's failure, Soviet engineers went back to the drawing board. The challenge was clear. Any spacecraft that hoped to reach the surface of Venus would need to be built like a deep-sea submarine. It would need to withstand crushing pressure and extreme heat for an extended period of time, and it would need to transmit data back to Earth before it inevitably failed. The early Venera landers had a relatively simple design. The core was a spherical pressure vessel made of titanium, about 1 meter in diameter. It was pressurized to 25 atmospheres on the inside to resist being crushed from the outside. Inside this sphere were batteries, instruments, and a radio transmitter. The lander had no rockets or thrusters. Instead, it used drag and a series of parachutes to slow its descent through Venus's thick atmosphere. But there was a problem with this approach. Venus's atmosphere is so dense that even with parachutes, the lander descended very slowly. Venera 4 had spent 90 minutes in the atmosphere, gradually heating up and being squeezed by increasing pressure, until it finally gave out. If the Soviets wanted to reach the surface, they would need to descend faster before the heat and pressure had time to destroy the spacecraft. For Venera 7, launched in August 1970, the engineers made significant changes. They reinforced the pressure vessel to withstand 180 atmospheres, massively overbuilding it to ensure survival. They also modified the parachute system. A cord was added that would keep the parachute reefed, preventing it from fully opening. This cord was designed to melt at 200 degrees Celsius, allowing the probe to fall rapidly through the hottest parts of the atmosphere and only deploy its parachute when closer to the surface. The spacecraft was also pre-cooled to -8 degrees Celsius before being released from its carrier spacecraft. This gave it a thermal buffer against the extreme heat it was about to encounter. On the 15th of December 1970, Venera 7 began its descent. The plan worked, mostly. The probe fell rapidly through the atmosphere, and the parachute deployed as intended. But then, just 3 kilometers above the surface, the parachute tore apart. Venera 7 went into freefall, hitting the surface at 17 meters per second. The impact knocked the lander onto its side, misaligning its antenna. The Soviets assumed the mission had failed. But weeks later, when engineers reviewed the recorded radio signals, they noticed something. A very weak signal had continued transmitting for 23 minutes after impact. Venera 7 had survived. It became the first human-made object to transmit data from the surface of another planet. The temperature reading was astonishing, 465 degrees Celsius. The pressure was 90 atmospheres, exactly as predicted by Mariner 5's measurements. Venus was even more extreme than anyone had thought. The Soviets had proven it was possible to reach the surface. Now they needed to figure out how to survive there. The problem wasn't just pressure. The titanium sphere could handle that. The real issue was heat. At 460 degrees Celsius, electronics fail rapidly. Batteries drain in minutes. Materials that are solid at room temperature begin to soften or melt. And once the spacecraft's internal temperature rose above a certain threshold, there was no coming back. For Venera 8, launched in 1972, Soviet engineers developed a new thermal management system. They cooled the descent capsule to -15 degrees Celsius before release. And they added something ingenious: phase change material. Inside the spacecraft were blocks of lithium nitrate trihydrate. This is a salt-like substance with an unusual property. It melts at 30 degrees Celsius, but the process of melting absorbs an enormous amount of heat energy, about 300 joules per gram. Once the material reaches its melting point, it continues absorbing heat without increasing in temperature until it has fully liquefied. This gave Venera 8 a thermal buffer. As heat from the Venusian environment penetrated the spacecraft, the lithium nitrate would slowly melt, absorbing that heat and keeping the electronics cool for as long as possible. The system worked. Venera 8 survived for 50 minutes on the surface, nearly twice as long as Venera 7. But the Soviets weren't satisfied. They wanted more time. They wanted better data. And most importantly, they wanted pictures. On the 8th of June 1975, Venera 9 touched down on the surface of Venus. This mission represented a complete redesign of the lander. The core was still a spherical titanium hull, but now it was surrounded by 12 centimeters of thermal insulation, a composite honeycomb material designed to resist both high temperatures and high pressures. A large thermal accumulator containing lithium nitrate trihydrate was installed, along with a circulating fan to distribute heat throughout the spacecraft. Most importantly, Venera 9 carried cameras. Designing a camera system that could function on Venus was an engineering challenge unlike any before it. The cameras had to be placed inside the pressurized vessel, but they needed a clear view of the outside. The solution was a periscope system. 2 cameras were mounted inside the lander, each with a periscope that extended through a thick quartz pressure window. At the end of each periscope was a lens that could rotate and scan 180 degrees. Each camera had a large lens cap designed to pop off after landing. The lander was pre-cooled to -10 degrees Celsius before separation from its carrier spacecraft. Then it began its descent. At about 50 kilometers above the surface, the parachute detached, and the lander used only air braking for the final descent. It settled onto the surface at around 7 to 8 meters per second. Once on the ground, the lens caps were supposed to eject. One of them did. The other didn't release. But one camera was enough. Venera 9 transmitted the first photograph ever taken from the surface of another planet. The image showed a rocky, desolate landscape. Sharp-edged stones, some as large as half a meter across, were scattered across the ground. The rocks appeared layered, possibly volcanic in origin. The sky above was bright, illuminated by sunlight filtering through Venus's thick clouds. The light level was roughly equivalent to an overcast day on Earth. The lander operated for 53 minutes before the heat finally overwhelmed its systems. The interior temperature had risen to 60 degrees Celsius by the end. But the mission wasn't ended by thermal failure. It ended because the orbiter that was relaying the signal back to Earth moved out of range. Venera 10 followed 5 days later. It landed in a different location and transmitted images for 65 minutes. Again, only one of its 2 cameras functioned. Again, the mission ended when the orbiter moved too far away, not because the lander had failed. For the first time, humanity could see what the surface of Venus looked like, and it was nothing like what anyone had imagined. The images from Venera 9 and 10 were groundbreaking, but they were black and white and relatively low resolution. The Soviets wanted more. Venera 11 and 12, launched in 1978, carried improved instruments but suffered the same frustrating problem. Neither spacecraft's lens caps released, no images were returned. But they did operate for 95 and 110 minutes respectively, transmitting atmospheric and surface data the entire time. The breakthrough came with Venera 13 and 14, launched in 1981. These landers were similar in design to their predecessors, but with key improvements. Soviet engineers had developed new heat-resistant materials and electronics that could function in extreme temperatures. Exotic lubricants based on molybdenum disulfide and microscopic metal flakes were designed to work at temperatures up to 1000 degrees Celsius. The amount of lithium nitrate phase change material was increased, and critically, the camera system was redesigned. On the 1st of March 1982, Venera 13 landed on the eastern edge of Phoebe Regio, a highland region of Venus. Both lens caps ejected successfully. The lander immediately began taking panoramic photographs. Unlike the black and white images from earlier missions, these were in color. They revealed a landscape of bedrock outcrops surrounded by dark, fine-grained soil. The rocks had a brownish-orange tint. The sky was a murky yellow-orange, the result of sunlight scattering through sulfur compounds in the atmosphere. But Venera 13 did something else unprecedented. It recorded sound. Microphones on the probe captured atmospheric wind noise as it descended and after it landed. These recordings also picked up sounds from the lander's own equipment. The impact of landing, the pyrotechnic ejection of the lens caps, and their impact on the ground, the drilling apparatus cutting into the surface. This was the first audio recording ever made on another planet. The sound is eerie, a low, rumbling wind, mechanical clunks and whirs, the hiss of the Venusian atmosphere at 92 atmospheres of pressure. It doesn't sound like Earth. It sounds exactly like what it is, an alien world. Venera 13 operated for 127 minutes, more than 2 hours. The temperature outside was 457 degrees Celsius. The pressure was 9 megapascals, equivalent to 89 Earth atmospheres. And throughout that time, the lander was drilling into the surface, analyzing soil samples, measuring atmospheric composition, and photographing its surroundings. A mechanical arm drilled into the ground and deposited samples into a hermetically sealed chamber, maintained at 30 degrees Celsius and 0.05 atmospheres of pressure. An X-ray fluorescent spectrometer analyzed the composition. The results showed the rock was leucitic basalt with high levels of potassium and magnesium, but only 1.5% sodium. This was Earth-like rock, volcanic in origin, similar to the basalts found on Earth's ocean floors. Venera 14 landed 4 days later, about 950 kilometers away. It also transmitted color images and operated for 57 minutes. Its sample analysis showed tholeiitic basalt, another common volcanic rock on Earth. The temperature was 465 degrees Celsius, slightly hotter than Venera 13's landing site. The pressure was 94 bars. One camera caught an unfortunate moment. When Venera 14 ejected its lens cap, it landed directly beneath the mechanical arm, designed to test the compressibility of the surface. Instead of measuring Venusian soil, the instrument measured the compressibility of the lens cap. Even on Venus, sometimes things just don't go as planned. The Venera missions sent back more than just photographs. They provided the first comprehensive ground truth measurements of Venus's atmosphere and surface. Venera 4 confirmed that carbon dioxide makes up 96.5% of the atmosphere. This was the first direct measurement of Venus's atmospheric composition. It also detected nitrogen, around 3 to 4% by volume, and trace amounts of water vapor, sulfur dioxide, and other gases. Venera 7 measured the temperature and pressure profile all the way to the surface, confirming the extreme conditions. It also provided the first evidence of high-speed zonal winds in the atmosphere, with velocities reaching 100 meters per second at altitude. This phenomenon, called superrotation, remains one of the most mysterious aspects of Venus's climate. Venera 8 carried a gamma-ray spectrometer that measured the amounts of potassium, uranium, and thorium in the surface rocks. These radioactive elements are important markers of a planet's thermal history and geological activity. Venera 9 and 10 provided more detailed gamma-ray analysis and the first images, allowing scientists to correlate chemical composition with visual features. Venera 13's soil analysis was particularly revealing. The high potassium content suggested that Venus's crust had undergone significant differentiation, meaning that lighter materials had separated from heavier ones over time. This is a process that happens on geologically active planets like Earth. The humidity measurements from both Venera 13 and 14 showed that the atmosphere near the surface contained less than 0.1% water vapor. For a planet that may have once had oceans, this is an astonishingly small amount. But perhaps the most intriguing findings came from later missions. Venera 15 and 16, launched in 1983, were orbiters rather than landers. They carried synthetic aperture radar systems that mapped the northern hemisphere of Venus at resolutions of 1 to 2 kilometers. The radar images revealed long rift valleys, volcanic features, and ridges and grooves that appeared to be the result of tectonic deformation. This was unexpected. Without water to lubricate tectonic plates, and without a magnetic field to suggest a molten core, Venus shouldn't have plate tectonics. Yet the radar images showed features that looked remarkably similar to tectonic activity on Earth. Here's where things get even stranger. At the surface of Venus, carbon dioxide isn't quite a gas anymore. It's something else. Carbon dioxide becomes a supercritical fluid above a critical point. 3 atmospheres of pressure and 304 Kelvin, about 31 degrees Celsius. A supercritical fluid has properties of both a liquid and a gas. It can dissolve materials like a liquid, but it flows and expands like a gas. It's dense like a liquid, about 67 kilograms per cubic meter on Venus, which is 6.5% the density of liquid water on Earth. At Venus's surface, with temperatures of 460 degrees Celsius and pressures of 92 bars, the carbon dioxide is well into the supercritical region. This means that Venus's surface is technically covered by a supercritical ocean. It doesn't have waves or a distinct surface the way water does. You couldn't swim in it, but it behaves more like a fluid than a gas. It transfers heat extremely efficiently, which is why the temperature on Venus barely changes between day and night. The supercritical carbon dioxide acts as a thermal buffer, distributing heat across the entire planet. Some researchers have suggested that this supercritical ocean may have once been even more liquid-like earlier in Venus's history, when pressures might have been higher. Computer models indicate that under certain conditions, clusters of gas-like bubbles could have formed in the supercritical carbon dioxide, creating structures that look like soap bubbles covered in a thick layer of liquid. Whether this ever happened on Venus is unknown, but the idea that Venus once had seas of liquid or near-liquid carbon dioxide is scientifically plausible. The geological features seen in the radar maps, the rift valleys and plains, could potentially be explained by the movement of this supercritical fluid across the surface, carving channels the way water does on Earth. Let's return to the engineering challenge, because understanding what the Soviets achieved requires understanding just how difficult it was. The longest any spacecraft has survived on the surface of Venus is 127 minutes. That's Venera 13's record, set in 1982, and it still stands today. The reason is heat. Even with thermal insulation, phase change materials, and pre-cooling, the extreme temperature eventually penetrates the spacecraft. Once the internal temperature crosses a certain threshold, electronics fail, batteries drain, and mechanical systems stop working. The Soviet engineers were aware of this limitation from the beginning. They designed the Venera landers as disposable probes. The goal wasn't to build something that could last indefinitely, it was to survive long enough to gather meaningful data. But what if you wanted to last longer? What if you wanted a lander that could operate for days or even weeks? NASA has been working on this problem for years. The key is developing electronics that can function at high temperatures without needing to be cooled. Traditional silicon-based semiconductors stop working at around 300 degrees Celsius because silicon transitions from a semiconductor to a conductor at high temperatures. To build circuits that can operate on Venus, you need a different material. Silicon carbide is one solution. It's a hybrid of silicon and carbon with a much larger band gap, meaning its electrons can absorb much more energy before it becomes a conductor. Silicon carbide semiconductors can function at temperatures up to 500 degrees Celsius or higher. In 2016, NASA's Glenn Research Center placed silicon carbide computer chips inside the Glenn Extreme Environments rig, a massive steel chamber designed to simulate the surface of Venus. The chamber can reach temperatures of 460 degrees Celsius and pressures of 90 bars, and it can mix gases to replicate Venus's atmosphere. The chips ran for 60 Earth days, continuously, in full Venus conditions. This was a breakthrough. The circuits weren't complex, only 175 transistors compared to billions in modern computer chips. But they were enough to handle sensors, data processing, and communications. Essentially, they had the computing power of the electronics used in the Apollo missions in the 1,960 seconds and 70 seconds. And that's enough to do science. NASA is now developing a small Venus lander called the Long-Lived In Situ Solar System Explorer, or LLISSE. It would weigh about 10 kilograms and carry sensors to measure temperature, pressure, wind speed, and atmospheric chemistry. Using silicon carbide electronics, it could operate for 60 Earth days or longer. That's 60 times longer than Venera 13. Despite everything the Venera missions taught us, Venus remains deeply mysterious. We don't know if Venus ever had liquid water oceans. Computer models suggest it might have, billions of years ago when the sun was cooler and Venus's atmosphere was thinner. If that's true, then Venus was once habitable, at least in the sense of having liquid water on its surface. We don't know what caused the runaway greenhouse effect that turned Venus into the hellscape it is today. Was it volcanic activity releasing massive amounts of carbon dioxide? Was it the loss of water, which would have helped remove CO2 from the atmosphere? Did Venus ever have a magnetic field to protect it from solar wind, and if so, when did it lose it? We don't know if Venus is geologically active today. The radar maps from Venera 15 and 16 and later missions like Magellan show volcanic features and tectonic-looking structures, but we haven't confirmed active volcanism. Some observations suggest recent lava flows, but these are difficult to verify from orbit. We don't know much about Venus's interior structure. Without seismometers operating on the surface for extended periods, we can't measure how heat and material move through the planet's mantle. We don't know if Venus has a molten core or if its core has solidified, and we don't fully understand the atmosphere. The superrotation, the planet-wide wind patterns, the sulfur cycle, the complex chemistry happening in the clouds, all of these phenomena remain poorly understood. There's also the question of the nitrogen gradient. Recent data analysis suggests that nitrogen concentration decreases from about 3.5% at 7,000 meters altitude to nearly zero at the surface. If real, this gradient could indicate active outgassing of carbon dioxide from Venus's crust, possibly from low-level volcanic activity. The flux of CO2 required to maintain this gradient is comparable to diffuse volcanic emissions from systems like Yellowstone on Earth. This would mean Venus is still geologically alive. NASA has announced 2 missions to Venus launching later this decade. Da Vinci Plus, the deep atmosphere Venus investigation of noble gases, chemistry, and imaging, will drop a probe through the atmosphere in 2031. During its hour-long descent, it will analyze trace gases, water vapor, temperature, and pressure. In its final 20 minutes, as it falls through the cloud deck, it will photograph a highland region called Alpha Regio before impacting the surface. Veritas, the Venus emissivity, radio science, INSAR, topography, and spectroscopy mission will use radar to map Venus's surface in far higher resolution than ever before, creating detailed 3D relief maps. It could identify safe landing sites for future missions. The European Space Agency has approved Envision, a radar mapping orbiter that will study Venus's surface composition and internal structure. Russia has been discussing Venera D, a return to Venus that would include both an orbiter and a lander. The lander would have a mission lifetime of about 3 hours based on battery capacity and traditional thermal management. But the real future of Venus exploration may lie in the technologies NASA is developing. Silicon carbide electronics, advanced phase change thermal systems, long-duration power supplies. If these technologies mature, we could have landers and even rovers operating on Venus for weeks or months. A seismometer operating on the surface for 60 days could detect Venus quakes, measure crustal movements, and determine whether Venus's interior is still molten. A rover could travel kilometers across the surface, studying different rock types and searching for evidence of past water. We could finally answer the fundamental question: is Venus dead, or is it still alive? Let's talk about something that often gets overlooked in the story of the Venera missions. Just how improvised and resourceful the Soviet space program actually was. When we think of space exploration, we often imagine cutting-edge facilities, unlimited budgets, and the latest technology. The reality of the Soviet program was very different. Especially in the early days, engineers were working with second-hand equipment, repurposed military hardware, and whatever materials they could find. The cameras on some of the early Venera probes were built using film stock captured from American reconnaissance missions. When Soviet forces shot down or recovered US spy planes, the film from their cameras was sometimes salvaged and repurposed for planetary exploration. It's a strange piece of history. American film, intended to photograph Soviet military installations, instead captured the first images of Venus's surface. The pressure vessels were welded by hand. The seals between different sections of the titanium sphere used gold wire gaskets compressed between bolted flanges. Gold was chosen because it remains malleable under high pressure and doesn't corrode in the presence of sulfuric acid vapors. But working with gold at these tolerances required extraordinary precision. A tiny imperfection in the seal could mean catastrophic failure during descent. The parachute systems were tested in massive vacuum chambers, but the conditions on Venus were so extreme that no Earth-based facility could perfectly replicate them. Engineers had to extrapolate from partial data, making educated guesses about how materials would behave under combinations of heat and pressure that had never been tested together. And yet, despite all these constraints, the Venera missions succeeded. Not every time. Many probes failed during launch, during transit, or during entry. The Soviet policy of not announcing missions until after they succeeded means we don't know the full count of failures, but the ones that worked spectacularly. Consider Venera 13's drill. It had to bore into volcanic rock at 460 degrees Celsius while surrounded by supercritical carbon dioxide at 92 atmospheres of pressure. The lubricants had to function in conditions where most materials would decompose. The drill bit had to remain sharp despite the heat. And the mechanical linkages had to transfer the sample to a sealed chamber without contaminating it with material from the lander itself. All of this was accomplished with 1,980 seconds technology. No computer modeling, no advanced simulations, just brilliant engineering, rigorous testing, and a willingness to try things that seemed impossible. We focused mostly on what happened after the landers reached the surface. But the descent through Venus's atmosphere was its own ordeal, and it revealed information just as valuable as the surface measurements. Venus's atmosphere is about 93 times more massive than Earth's. It extends much higher, and it's structured in distinct layers, each with its own characteristics. At the top, above 100 kilometers, the atmosphere is thin and relatively cool. This is where spacecraft first encountered drag during entry. Venera probes hit the atmosphere at speeds around 11 kilometers per second, and the initial deceleration was violent. The heat shield had to absorb temperatures exceeding 11,000 degrees Celsius as friction converted kinetic energy into heat. Between 70 and 50 kilometers altitude, the landers entered the cloud deck. This is where the sulfuric acid droplets are concentrated. The clouds are not uniform. They're layered, with different particle sizes and compositions at different altitudes. Some Venera probes carried nephelometers, instruments designed to measure cloud particle density and size. The data showed that the largest droplets, up to 10 micrometers across, are found in the middle cloud layer around 50 to 55 kilometers. Below the clouds, the atmosphere becomes increasingly dense and hot. At 30 kilometers, the pressure is about 10 bars, and the temperature is around 200 degrees Celsius. This is where the parachutes were designed to detach, allowing the landers to fall faster using only air resistance. The final descent from 30 kilometers to the surface took about 30 to 40 minutes. During this time, temperature and pressure increased exponentially. The landers were transmitting continuous measurements, building a detailed profile of the lower atmosphere. One of the key discoveries was the wind profile. At altitude, Venus's atmosphere rotates around the planet in just 4 Earth days, a phenomenon called superrotation. Winds at the cloud tops reach speeds of 100 meters per second or more. But as you descend toward the surface, the winds slow dramatically. By the time you reach the ground, wind speeds are only about 0.5 to 1 meter per second. This creates a paradox. The upper atmosphere is moving incredibly fast, but the surface is nearly still. What drives this motion? How is energy transferred between layers? These questions remain partially unanswered, though some researchers believe convective cells and atmospheric waves play a role. The Venera missions also measured the composition of the atmosphere at different altitudes. Carbon dioxide dominates everywhere, but the concentration of trace gases changes with height. Sulfur dioxide is more abundant at mid-altitudes. Water vapor, though scarce, is slightly more concentrated near the surface. These gradients provide clues about chemical reactions happening in the atmosphere and possible interactions with the surface. In 1984, the Soviet Union launched 2 spacecraft called VeGa 1 and VeGa 2. The name is a portmanteau of Venera and Gale, the Russian word for Halley, because these spacecraft had a dual mission: drop probes at Venus, then continue on to fly past Halley's comet. Each VeGa spacecraft carried a lander similar to the Venera 13 and 14 design, but they also carried something new: balloons. The French space agency, CNES, had designed a balloon system specifically for Venus's atmosphere. The concept was to deploy a helium-filled balloon at an altitude of about 54 kilometers in the middle cloud layer, where temperatures are relatively moderate, around 40 degrees Celsius, and pressures are only a few bars. The balloons were made of Teflon-coated fabric, about 3.4 meters in diameter when inflated. Each carried a gondola, weighing about 7 kilograms, equipped with instruments to measure pressure, temperature, wind speed, light levels, and atmospheric composition. On June 11 and 15, 1985, the VeGa balloons were successfully deployed. They drifted with the Venusian winds carried by the super-rotating atmosphere, completing nearly half a circuit around the planet over the course of 46 hours before their batteries ran out. The data they sent back was extraordinary. The balloons revealed that Venus's cloud layer is turbulent and dynamic. Vertical winds were stronger than expected, with updrafts and downdrafts exceeding 3 meters per second. These convective motions indicated that energy was being transported upward from the hot surface below, driving circulation in the clouds. The balloons also measured lightning, or rather, they detected electromagnetic signals consistent with electrical discharges. Whether Venus has lightning comparable to Earth's thunderstorms remains debated, but the VeGa data suggested that electrical activity does occur in the clouds, possibly triggered by collisions between sulfuric acid droplets or by volcanic gases rising from the surface. Temperature fluctuations were also surprising. Over the course of a few hours, the balloons experienced temperature swings of several degrees, indicating that the atmosphere at that altitude is not stable or uniform. There are pockets of warmer and cooler air, mixing and circulating in ways that weren't fully understood. The VeGa balloon missions were a triumph of international cooperation. French engineers designed the balloons, Soviet engineers integrated them into the spacecraft, and tracking stations around the world monitored the signals as the balloons drifted around Venus. It was one of the few instances during the Cold War where space exploration brought nations together rather than driving them apart. Here's where we need to tread carefully, because this is a topic that can easily veer into speculation. In 2012, a Russian scientist named Leonid Ksanfomality published an article claiming to have found evidence of life in the Venera images. He pointed to certain objects in photographs from Venera 13 that appeared to emerge, fluctuate, and disappear between frames. He suggested these could be living organisms, adapted to Venus's extreme conditions. The objects included what he called a disk, a black flap, and a scorpion. According to Ksanfomality, their changing positions implied movement. Engineers familiar with the Venera probes quickly identified the disk as one of the ejected lens caps. There were 2 lens caps, and they landed in different places, creating the illusion of a single object that had moved. The other objects were attributed to image processing artifacts and noise. They don't appear in the original photography, only in enhanced versions. The scientific community largely dismissed these claims, but the episode raises an interesting question. Could life exist on Venus? Not on the surface. That much is certain. The temperature and pressure are too extreme, and there's no liquid water. But some astrobiologists have suggested that life could exist in the clouds, at altitudes where conditions are more temperate. At 50 to 60 kilometers above the surface, the temperature is around 20 to 40 degrees Celsius. The pressure is roughly 1 bar. Sulfuric acid droplets dominate, but there's also water vapor. In theory, microbial life could survive in these droplets, using chemical energy from sulfur compounds or absorbing sunlight for photosynthesis. There's even some observational support for this idea. Measurements of sulfur dioxide concentrations in Venus's atmosphere show strange variations that are difficult to explain through chemistry alone. Some researchers have proposed that biological processes could be consuming or producing sulfur compounds, though this is highly speculative. In 2020, a team of scientists announced the detection of phosphine gas in Venus's clouds. Phosphine is a molecule that, on Earth, is produced almost exclusively by biological processes or industrial activity. Its presence on Venus, if confirmed, would be difficult to explain without invoking either unknown chemistry or biological sources. However, subsequent reanalysis of the data cast doubt on the detection. It's possible the signal was misinterpreted or contaminated by noise. As of now, the phosphine claim remains unresolved. The point is this: Venus may not be completely dead. The clouds, at least, remain a place where we cannot rule out the possibility of life. It would be life unlike anything on Earth, adapted to float in sulfuric acid droplets. But the chemistry of life is remarkably flexible. Future missions carrying more sensitive instruments could settle the question. But for now, it remains an open mystery. The last Soviet probe to reach Venus's surface was Venera 16 inches 1983, conducting radar mapping from orbit. The last lander was Venera 14 inches 1982. The VeGa missions in 1984 were the final hurrah. And then, nothing. For decades. Why? Part of the answer is economics. The Soviet Union was facing increasing financial strain in the 1980 seconds. Space exploration, while prestigious, was expensive. Venus missions, with their complex engineering requirements and high failure rates, were particularly costly. By the mid-1980 seconds, Soviet priorities were shifting. The Mir space station program was taking up resources. Plans for Mars missions were being drawn up. Venus fell out of favor. The collapse of the Soviet Union in 1991 essentially ended Russia's planetary exploration program for years. Budgets were slashed. Expertise was lost as engineers retired or moved to other fields. The infrastructure that had supported the Venera program decayed. Meanwhile, NASA's focus had shifted to Mars. The Viking landers in 1976 had captured the public imagination. Mars seemed more hospitable, more Earth-like, more likely to have hosted life. Venus, by comparison, seemed like a dead end. There was also a technological barrier. The Venera missions had pushed 1,970 seconds and 80 seconds technology to its absolute limit. To go beyond 2 hours of surface operation would require fundamentally new approaches, new materials, new electronics, new power systems. Those technologies didn't exist yet, so Venus was left alone. The Magellan radar mapper in the 1,990 seconds provided detailed surface maps, but it never descended through the clouds. European and Japanese orbiters followed, studying the atmosphere from above, but not venturing below. It's only in the last few years that interest has returned, partly because the technology is finally catching up, partly because scientists have come to realize that understanding Venus is critical to understanding Earth's climate, and partly because the discovery of thousands of exoplanets has made Venus-like worlds suddenly relevant again. Many of the rocky planets orbiting other stars are likely more similar to Venus than to Earth. If we want to understand those distant worlds, we need to understand Venus. There's something haunting about the Venera photographs. They're grainy and distorted, artifacts of 1,970 seconds and 80 seconds technology transmitted across tens of millions of kilometers. But they show a world that no human will ever visit in person. The landscape is alien, yet familiar. Rocks, dirt, a horizon. If you saw these images without context, you might think they were taken in a desert on Earth. It's only when you learn about the temperature, the pressure, the supercritical carbon dioxide ocean you'd be standing in, that the alienness becomes clear. The Soviets sent machines to hell and brought back pictures. They proved that even in the most hostile environment we know of, it's possible to survive long enough to learn something. Every rock in those photographs tells a story. Every crack in the ground is a clue. Venus was once different. It may have had oceans. It may have had a climate not unlike Earth's. Something changed. And until we understand what that something was, we won't fully understand our own planet's future. The Venera missions were an achievement that deserves more recognition than it gets. In the West, they were overshadowed by the space race to the Moon and the Viking landers on Mars. But in terms of pure engineering difficulty, landing on Venus and operating there for even a few minutes was as impressive as anything NASA accomplished. The last signals from Venera 13 and 14 faded out in 1982. The landers are still there, on the plains of Venus, slowly being corroded by the atmosphere. One day, perhaps, a future mission will find them, these ancient artifacts of humanity's first steps onto another world's surface. For now, they rest in the heat and the darkness and the crushing pressure, monuments to what humans can achieve when we refuse to accept that something is impossible.